It's short. It's real short.
Are you sure his questions are easy?
Yeah, we took his course last semester.
Oh, his questions were easy.
His
but
questions are easier than Kumar's, so.
Yeah, let's see. Where is it?
Cool.
Down
Slideshow.
presentation. Yeah.
Just there.
Just where?
Yeah.
Yay.
Like,
Oh, this is too big. I don't know if the camera
What do you
can.
mean?
I know. I think I got it.
everyone has been presenting like this. So.
All right.
It's all good.
Okay. Cool. So, this paper, to sum it up, is kind of looking at the elastic modulus of amorphous polymer thin films. And I mean by thin, I mean really, really thin, and we'll get to that. So basically, it turns out that when it comes down to very small length scales, polymers behave differently than they do in the bulk. And this is largely due to a couple of different types of confinement effects, right? So what this paper goes into is seeing if, and this is only like one sentence. Wait, did I hit record? Yeah, I did. Yeah, so this is like only one sentence in the entire paper, but they're basically trying to see the effects of thickness and the effects of thickness on the mechanical properties of these very thin film polymers, and the effect of undercooling below the glass transition temperature also has on that mechanical property, right? They're also seeing how that level of undercooling increases the effects or decreases the effects of the overall material within the film that is affected by larger degrees of freedom towards the surface. So we'll get into that, and yeah, what this basically does as far as characterization goes is it just pretty much does some material testing with wrinkling properties, right? So usually it's like these materials or it's so thin that you can't really do mechanical testing on them, it seems. And instead, they get a substrate of very low modulus and wrinkle that substrate like equivalently for each of the polymers and then they see how these things wrinkle, and then they relate that to elastic modulus.
How do they wrinkle them? How do they wrinkle them? Like more specific.
I think they must compress them, no?
They clamp them
Yeah.
on two sides, and then they apply like some frequency of vibrations to cause the wrinkling. Yeah, Sukuk taught it too.
Okay.
Yeah.
Okay.
So this also has ellipsometry, and that's what I was saying. Like
Yeah,
they use ellipsometry to calculate the TG, which is interesting. But yeah, I would like to learn more about that.
I didn't get to the ellipsometry for this.
Sure.
But yeah.
Also, for the substrate, you said it was low modulus?
Yeah,
Elastic
it was
modulus? What modulus?
low elastic
Elastic
modulus.
modulus.
Okay.
Yeah, and I think it was some sort of silicide or something like that. Let me see.
Yeah, I don't remember the substrate they used.
Maybe I have it in my.
I have this paper here. Though. It was very interesting, actually. I don't think. Okay, it's here.
Did I have it? Yes, I did.
I believe it was some sort of sidelong same, but there's some sort of.
PDMS.
Oh.
Yeah.
Oh
that
yeah,
one.
it is on PDMS.
PDMS.
Oh,
Yeah, you can
right.
continue.
Okay.
Because they also said something about the substrates being rigid in previous experiments, right?
Mhm,
And that's
mhm,
why this
mhm.
was so difficult.
Yeah.
Yeah.
So
Yeah.
they
There's.
used PDMS.
They're
Yeah.
like totally shitting on the previous experiments at the beginning, and they're saying that none of them kind of added up.
Yeah.
There's no sort of like agreement within any of the experiments, and then newer sort of things came along, and that way they could actually test these materials better. So yeah, I guess the wrinkling things came later on. Why is this thing just going nuts on its own? Give me a second. Okay, so just to add, as far as this paper, I think the most important thing to kind of take out of it, even though it's only two sentences, is like the Carl Jacob knowledge on doubly left equations and the time temperature superposition. And as far as background to this, what TG is and how that, like a polymer molecular weight and molecule sort of design and everything can affect that. And so I'll show you the applications of this, but for now, I just want to like add some cool things that I saw out of the paper, right? So because of the free surface effects, which I'll go into, at some point, at some thickness, polymers don't wrinkle under these tests because they're super flowy, and because of that, they just don't have any sort of modulus at all, it seems, so they don't wrinkle, right? They flow more.
Right.
And yeah, as I said before, wrinkling polymers can give you that modulus of the specific film. And because of the surface-free effects, as I previously said, all polymers are a little squishy on top. And this happens even in bulk polymers. You could have the surface sort of seeing these effects up to like 5 nanometers, or depending on the polymer itself, it could be deeper.
That's interesting.
So this paper story kind of starts off with pretty much nano patterning of polymer films, right? So what happens in nano patterning is you start off with a silicon wafer, and you spin coat a polymer on that silicon wafer, and you press it with your patterning stamp. Because microelectronics have gotten like much smaller, and they probably started off small, the patterning length scale is within the same length scale that you get with the molecular length, right? So you basically wind up with confinement effects within these patterns that heavily affect the mechanical properties. And because you have these deviant mechanical properties, you can't really estimate how your patterning is going to go, and negative effects down the line, right? So if you don't wind up with the properties you anticipated, there will be all sorts of problems. And so right here off to the bottom right, you can see, I kind of just drew that up, that yeah, like if you look and zoom into one of those, what we wind up with are these molecules that are in chain length on the same length scale as the patterning. So because of a lot of these surface-free energy effects, the polymers have a lot more degrees of freedom at the surface. And depending on the polymer and the temperature, this effect can go deeper into the bulk of the material. So if you have a polymer that has a lower glass transition temperature, and you are and you decide to change your manufacturing from a polymer that has a higher transition temperature to that polymer that has a lower transition temperature, you should probably anticipate these effects occurring more. So these effects lead to decreased flow resistance and residual stress in the molded material. And because the patterning in these is kind of difficult to study, the best way to confine the polymers that we have is by making very thin films. And in this paper, they spun coat these films onto a substrate. And mind you, there are substrate and surface interactions, like substrate air, or like film air, film substrate interactions, but they mostly focused on the film air interactions. So yeah, that's why they chose thin films to sort of kind of narrow down that polymer and kind of keep it within a certain space. So yeah, what they're trying to kind of gauge from this is, first of all, establishing when these confinement effects occur and how these confinement effects dominate the overall properties of the bulk in these polymers. So what we have are changes in mechanical properties when you decrease the film thickness. So if you wind up at a very thick film, say 200 or 300 nanometers, then slowly stepwise go down, at a certain point, depending on the polymer and depending at the temperature that you're working at for all these experiments, you will have a relatively sharp transition in the thickness in which all these properties sort of tend to deviate. So you get a decrease in elastic modulus usually. And yeah, as I said, it depends on the polymer too. So what they wanted to test out is they wanted to test out how undercooling effects below the glass transition temperature affects the thickness of that affected area. And what they sort of anticipated, and what wound up happening, was that polymer at a certain temperature, say okay, the closer you are to the glass transition temperature, the thicker that layer will be. But they didn't do this like a normal person would, because they said that instead of changing the temperature of the experiment that they had, they changed the material. What the heck? What happened? That's not good. Okay, cool. I think this is, what do I do? I don't know technology.
Yeah,
I'm just
no
holding
idea.
a big chocolate bar right now. I don't know what's happening.
Maybe you can pause it. I don't know.
If I paused it, I would rather just keep on going so I don't have to make a video.
15 more minutes.
I don't know. Can you click the power button there in the bottom front corner?
Let's see that.
Yeah.
That should do things.
This paper is actually long. I don't know.
I mean, I could.
Okay.
Oh, well, okay.
Oh.
I could just go straight to PowerPoint again, right?
Go back to PowerPoint.
No, there's a
PowerPoint.
PowerPoint thing
Oh.
down there. Yeah. Oh, it was just a matter of it just shut off on its own.
Yeah, it just went to sleep.
Yeah.
Hello.
Thank you.
Yeah.
Yes. I did not.
Change these?
What
I
happened?
tried. It is not.
Oh, is it cold in here?
Yeah.
Oh, well.
Let's go.
They said it.
Come on, wait for the
I think there's no heat.
Yeah, Thomas.
Yeah. Okay. Well, anyways, because this is where my understanding sort of, because they only explained it in 2 sentences, they're kind of trying to see whether or not these thin films adhere to the WLF equations and the time temperature superposition. So, yeah, as I was saying, okay, as I was saying, instead of changing the substrate temperature and testing the material at different temperature, the same material, the same molecular weight, they decided to vary the material by adding longer side chains to polymethyl methacrylate, right?
Yeah.
So what they wind up with is the longer the side chains, the lower the glass transition temperature of the material. And so this, if you have a set temperature to work with, can relate to the decrease in undercooling of below the glass transition temperature for the model system. But
That's
the
what they call the quench depth.
the quench depth. The thing is that there's 2 depths here. There's the depth of the thickness of the
Yeah,
thing, and then there's like the quench depth. And I never used quench depth before.
Yeah, I think, yeah, so mainly they were trying to say like they varied the tail length of the PMMA, yes, to be able to vary the glass transition temperature.
Yeah.
Basically, since it's the same material, you're just changing the tail length, you can then be able to measure like the effect of the quench depth on
Yeah.
literally the same material.
They say it's the same material,
Yeah,
but to
yeah,
me, it's
yeah.
not the same material.
Yeah.
And they kind of play sibling here and say, well, they did it, and why can't I, right? Because they're kind of referencing to all the old papers that chose completely different materials with different molecular weights to test this theory out. But to
Okay.
me, there are going to be different confinement effects when it comes to different chain links, because there's going to be different interactions to different extents in all these materials, which is why I don't really like this paper.
Yeah.
So, and there's different molecular weights. They could have controlled that.
Yeah, at the beginning, I also thought about like, why are they? Because they talk about TG. Like when they start the paper, they talk a lot about TG,
Mm-hmm.
and then they switch to the modulus,
Yeah.
right?
Yeah.
And I'm like, why are they like referencing this on TG, right?
Yeah.
Maybe when you make reference to the WLF equation, you need TG to actually make that equation work, right?
Mhm.
Reference temperature. But then they were trying to say like the confinement effects as a result of TG are well studied, whilst the confinement effects and how it affects the
No.
modulus have not been studied.
They're
well.
saying how not much has been studied close to TG, and they're saying that all these experiments in the past have been done well into the crystallization
Mhm,
temperatures, right? So
Yeah.
they wanted to see particularly how getting close to TG would affect the thickness of that.
Yeah. I get your point, but what I'm saying is like they were talking about like the confinement effect and how it relates to TG, right?
Oh yeah,
Has
yeah.
been studied in general, but like this paper is focusing on the modulus and TG.
Yeah, because I
Yeah.
think they're relating modulus to
Yeah.
when the transition occurs for these thin films.
Yeah.
So what happens is that at a certain thin film thickness, you have a drastic change in modulus of elasticity. And this modulus of elasticity is derived from the folding, a wavelength of the films that you get from the experiments.
Yeah.
This is like the equation that you get in EF is the film modulus, right? And ES is the substrate modulus.
Yeah.
So they use that as a measure of transition, right? The thing is that these transitions occur previous to the glass transition temperature and also are dependent on the thickness of the film, right? And I'll get into that later because that's kind of modeled into sort of a bilayer system where you have the squishy layer on top and the bulk film on the bottom, right? But we'll get into that. But for me, it's kind of, like I said, it's difficult to gauge. It's not a direct comparison because the materials are different, right?
I have a quick question. They mentioned quench depth being TG bulk minus T. Is T the temperature that they're doing the experiment at?
Yes, and TG bulk is the thick film. Let's say thick film where the bulk property of the material. Yeah. Okay.
But they are conducting experiments at a set temperature.
They're conducting experiments at room temperature, but the way they're decreasing the undercooling, or T minus TG, is by varying the molecular structure so that we have different glass transition temperatures.
So is T room temperature then?
Yes.
Okay.
It's always room temperature.
Okay. Right.
And that's why I don't like, because, I mean, they're just like, it's too hard to keep the substrate up, I'm tired, and they decided not to do it. Oh, yes. So anyways, this is where the cringe comes in, okay? But yeah, they chose all these polymers, polymethyl methacrylate, polyethyl methacrylate, polypropyl methacrylate, and all the other things, and I just added that thing. I don't know.
Why did they use polyacrylate? Is that the term for all of them?
Why they added them? Why they used them? I think.
Yeah. Okay. Someone has no background in chemistry. What's a polyacrylate or polymethacrylate? Why this class of materials?
I think.
It just defines the CH3.
Yeah.
So the CH2 and the CH3 and the C, that's the same. That's the methacrylate, not the methacrylate part. That's the the carboxyl acid.
Yeah.
Oh.
So that's that part. So you're always gonna have that, and then once you get past that section to the O,
Yeah.
and then for the first one you have CH3, that's methyl. For the second one you have CH2, CH3, that's ethyl. Then for the next one you have isyl, you have propyl. So we don't know which direction the purple is, but it's like a little thing. Then we have benzyl. So just look at the last subgroup,
Okay.
and that is what changes. Everything else.
Oh,
is
that's
the same.
what they're changing is that
Yeah.
that end group. Okay.
But the backbone, everything above that oxygen is going to be the same.
Yeah. Okay. I see.
Yeah.
That makes sense.
So
Thank you.
the way this sort of affects the glass transition temperature is because with the increasing size of the side chains, you kind of have more free volume in the polymer, right? And so because of that, it more readily flows when heat is inputted. So what you wind up with, and then oddly enough, these same entanglements, this same free volume and extra chain space leads to entanglements later down when you're doing melting temperature, and usually an increased chain length increases the melting temperature because of these entanglements. So yeah, I worked like 30 minutes on that bird. Anyways, it's terrible. But anyways, yeah, as far as the results, yeah, we finally get into results. So what they kind of started off with at sort of the introduction of the results is that previous studies had shown that a lot of these squishiness effects start at the free surface because there's more degrees of freedom for the polymer chains, and that kind of is better for cooperative motion of the polymers. And cooperative motion being that when polymers become a little more loose and unbound to their bulk because of whatever an increase of degree of freedom because of heat, or in this case because of a free surface, polymers kind of move in groups and start to flow a little more, right? So as you approach the glass transition temperature for these materials, this region just deepens within the thin film. So say you have a film that's 100 nanometers, the thickness at which you see the effects, say at 20 or 30 degrees, so you say at 30 degrees of undercooling, can be like 80, whereas at like 5 degrees of undercooling, it'd be like 40, right? So that's what they're kind of trying to tell you here with all these graphs is, and along with that, they have like the sort of, wrinkling effects of the polymers and how the more the wrinkles you have, the lower the modulus is, and lower modulus polymers were closer to the glass transition temperature. So the longer the chain length on these molecules, the less the elastic modulus. And we can also have, you can see the onset of these moduli occurring for all these things, and the overall thickness of the material. So yeah, the onset starts a lot earlier for these other polymers.
And just like a general thing, once you get above that glass transition temperature, you would expect the elastic modulus to be super low.
Yes, yeah, pretty much. Actually, just you just assume like a very pretty much.
Okay.
Yeah, I think like let's go back to fundamentals, right? So like glass transition temperature. Below glass transition temperature, where are you? Like what kind of structure? Right. Crystalline, right?
Yeah.
And then between like your glass transition and your melting temperature, you are in like the rubbery state, right?
Yeah.
And then you go to the liquid, right?
Yeah. So
like when I was reading this paper, I had to go back to that and then try to now visualize it. So once you're at glass transition temperature, you're now moving from a more ordered system to like a more fluid system. So in that rubbery state, a lot of things can happen, and that's what they try to state. As you go closer and closer to your glass transition temperature, there's more mobility and other things.
Which direction are we coming from? Are we coming from below the glass temperature or above?
we're coming from below, from the crystalline state.
You're
Yeah.
warming it.
Yeah.
You're
And
warming it up.
Usually
they're not warming anything. They're just taking they're at one temperature.
Yeah.
But the
Yeah.
materials that they're choosing transition
Yes.
at progressively lower temperatures.
And that's the thing.
Okay.
So what I did was like I calculated like the quench depth for like each of these, right? Because like you have all these temperatures and you like subtract it from room temperature.
You can
basically.
calculate that?
It's-
Just
yeah.
the quench
Yeah,
temperature.
the quench depth, right?
Okay.
And then you can now see how close you are. Like I just built a trend and say, okay, as we maybe increase from maybe here to here, I'd have to check my stuff. But then you see that like as you increase, maybe you are either closer to TG or you are further away from TG. And when you compare that to the results they find, you'd see that it actually affects like the modulus or that critical thickness that you get to before the deviations. Okay,
Got it.
but that's how I do it.
Yeah. So let's see. So one question that they sort of asked in the paper is, are these effects starting from the surface, and do we have a heterogeneous sort of transition between super squishy to super bulk and super hard, or does the material as a whole behave a certain way, right? And this is a question that they posed, but then to kind of review this or test this, they chose a bilayer model, which is kind of strange to me, because if they're going to test whether or not a material is homogeneous or heterogeneous, to test it, they're testing it out by assuming a heterogeneous system. So I don't know, Jude, what did you think about that?
Is it where they go to the PIBMA stuff? Or which one?
This is
Yeah.
when they start doing the model, right?
Yeah.
And I think it was, oh, here we go. In an
Yeah.
effort to quantify the free surface effects. However, it is not clear if this change in moduli is homogeneous though.
Mm-hmm.
The film, homogeneous through the film, or is a surface interface effect. And then in order to test that, they choose a bilayer model. But they're already assuming that it's like heterogeneous.
Yeah.
So to me, I found a flaw in that,
Yeah.
right? Because they could have tested it a different way.
Well,
Which,
I mean, they have to separate the top and the bottom because they're gonna have different.
In some
elastic
way.
content.
1, 0.
I guess they're kind of see if like one is completely dominant at
Yeah.
at all times
Yeah.
or something.
That's how so I literally drew like my own bilayer model with it, and I was like, okay, so they are trying to say like this is the HF minus the delta,
Yeah.
and then they have like the delta, and so they come from the bulk. So like this is what I drew. So they come from like here, right?
That's so
shit.
funny.
Mm-hmm.
And so as you go higher, there's a minimum critical thickness, right? Where then you go from this to where the deviations start to occur.
Mm-hmm.
That's how I see it, like as they use a bilayer model to kind of separate like these effects and see when the delta actually starts
I see.
taking an effect. Yeah.
Yeah. So I guess if the squishy layer were to go
Yeah.
throughout the entire material,
Yeah.
then yeah, you would see.
You would not be
It
able
would
to
be-
identify.
But it would also be homogeneous stuff.
Mm-hmm.
Okay, but they actually got that. Let me see. They got a couple of things happening from this.
Mm-hmm.
First of all, they found that the bulk properties are mirrored by both the surface, the close to the surface, the squishy surface properties, and the overall bulk. Okay, so the overall properties are dominated by like the bulk and the squishy surface, right? And
Right.
the squishy surface extends as the as you get closer to the glass transition temperature from crystallization phase, right? So the thickness of the film comes in to where this is always extending at a certain rate when as it approaches the glass transition. But at a thinner film, that squishy thickness is proportionately more than if you had a very thick film. Like I said, every polymer has a squishy surface, but if your polymer is really thin, that squishy surface, which can be constant depending on the temperature, if you keep the temperature constant, will just proportionately be more or less dominant. And that's the first thing that we kind of come to when we have the progressively thinner films. Is it a function of just the film? It's not really a function of the overall squishy layer increasing. It's just that the polymer film is decreasing in width overall. So of course the squishy properties are going to start dominating. But yes, then of course we also have the thickness of that squishy layer increasing with the approaching of the glass transition temperature.
Yeah.
So both of those things were already kind of proven experimental. Well, yeah, the first one was kind of proven. The second one was proven experimentally, as in the thickness increases, right? But then they kind of had a proportional thing going on, and that's how they sort of explained it.
And I
with this
think, like,
model.
theoretically, as we are saying, like, as you are going closer and closer to TG,
Mm-hmm.
right, then you are getting closer to a region which is less ordered
Yes.
and more fluid. So
Mhm.
it makes sense that there's going to be more deviation in, like, the behavior, or you're going to have a greater thickness of your region, which is different from your bulk situation.
Exactly, yeah. So they had these equations kind of pulled up, and there are some scary looking equations.
Like, where do you start from?
So I would say we start from like cooperative rearrangement, which is the thing where I was saying that polymers tend to sort of agglomerate together and kind of break free in kind of groups when we start to approach glass transition, or when we start to approach more freedom in general, as in the free surface. So we have this cooperative rearrangement sort of term, which is inputted in the couple of spots of this equation. And then we have the film thickness and the bulk modulus and delta, which is the, what was it delta again?
Yeah, I wrote it down. I use it a lot, but I think delta is
small
like
delta. Here we go. I think
the thickness of that layer.
yeah, the surface, the thickness of the surface layer,
yeah,
the squishy layer.
the thickness of that layer.
Yeah.
That's what I use.
Okay. So then, pretty much this equation serves well because now you can correlate the undercooling to the squishy thickness, and you can change your fabrication processes to maybe work at different temperatures, or choose different materials that can sustain the temperatures that you're working at. So yeah, pretty much. Oh yeah, and this is also an interesting thing. So at some point, obviously at or near the glass transition temperature, the squishy layer just extends so far that pretty much the entire film is squish. So yeah, this is where the WLF equation sort of comes in, and they legit just mentioned this once in the conclusion, which kind of sucks because they didn't really kind of express their thoughts more on it. But from what I think, it's more of like the WLF equation and the time temperature superposition kind of relates the increase in temperature to the change in viscoelastic properties, but sort of has a relaxation modulus as kind of like a constant with all those different, it's like an increase in temperature versus like the relaxation modulus and the time in which you test it, right? But the thing is, this is where I have trouble kind of relating it, because from what I can think this paper is saying, they're just saying that the WLF and the time temperature superposition doesn't really work in the really small scale cases, or it may, but there's also a new feature that is this can change with the thickness, right?
Yeah.
So because now we have another thing that's affecting these parameters, not just temperature, now we have film thickness, it doesn't completely follow the time temperature superposition, and the WLF equation falls apart. And I think that's what they meant. What do you think, Jude?
Yeah, that's what they say. So like in like the last but one sentence, they say that additionally changes in the modulus of the PMA thin films do not directly correlate to the thin film TG. This result raises questions to the applicability of fundamental concepts such as the WLF equation that relate TG to other physical properties. Yeah, so they are trying to say like, yes, as we go to these nanometer scale thicknesses, you may not necessarily be able to use this WLF equation to see the effects that occur in that system.
Because we're already really flowy, kind of,
Yeah, and you see like in the WLF equation, this shift factor, right? What did we relate it to in class? I think it was the viscosity.
Yeah, it was viscosity.
Right. And I think, and viscosity is like rubber elasticity property of materials. And so like, even though like the temperature side is cool, that mechanical property on your left would not directly vary because of how small, that thickness, thickness dependence. I think that's what you're trying to come to.
I think that's what I came to as well. But yeah, so that's pretty much it for this paper.
Yeah, there's lots of
possible future work. Okay, so in this paper they kind of wanted to check out like local distributions of moduli, like possibly seeing, I don't know how they would even do this, but I guess they would probably do like nano DMA or something like that. And
nano
they would,
DMA could say.
And they'd probably just see like, how does this change with along the surface, if there's any variations. And they want to know like the origin of this relationship and whether it's driven by the inherent mobility of surface chains, right? But I really do think that for future work, they should focus on one polymer system and try to maybe just adjust the heating, the substrate temperature for the heat. Because that way we could just directly relate and not have molecular kind of,
I like a question that Isabella asked, like, why did they decide to do it on PMMA? Like, aside all the polymers they could use.
PDMS?
No, PDMS was like a substrate.
But why did they do
that? So why did they use PMMA?
I think
that was the substrate.
I think maybe it's just because they could vary the tail length thing to be able to show.
PMMA a base system?
So like
PMMA is
PMMA is like what they are saying.
They started with PMMA and they just kept on adding side chains.
They added side chains to it.
But the main function of that to decrease the glass transition
temperature
as a way to measure undercooling at a set temperature.
Yeah. Okay, so what's undercooling?
Undercooling is at what temperature you measure. Okay, undercooling is the temperature at which you measure with relation to the glass transition temperature of that material. So say the glass transition temperature of a material is like 40 degrees and you're measuring it like 20 degrees, then the undercooling is 20 degrees.
You're measuring at 20 degrees?
Okay,
or...
let's say 25 degrees. Okay?
Why,
So-
why
know-
that, why that's
Yeah.
important?
It's
Wait, so-
important because the closer you get to the glass transition temperature in these materials, from colder to hotter, that is, if you start at a more ordered glassy regime, and you progressively get closer to that glass transition temperature, then there will
Is
be like more
undercooling the
chain
gap?
freedom. Yeah, undercooling is the gap.
Okay.
So then there's more like chain freedom and an increase of the squishy, lesserly ordered region.
I think the best way to explain this is with the DSC.
Yeah.
Right, because like when you heat it up to like to melting temperature,
Mhm.
right? So your melting temperature is like 160 degrees Celsius,
Mhm.
and then you pass maybe your TG at like 100 degrees Celsius.
Yeah.
When you start cooling, there's some gap because of maybe like the chains are trying to rearrange themselves and all that.
Mm-hmm.
So when you heat, in your heat, you probably see the TG at 80 degrees Celsius.
Yeah.
But when you're cooling, you probably see it at maybe 70 degrees Celsius. So that
Do
gap
we have
is
like a marker?
Oh, so that's the gap.
yeah.
Wait, do we have like a marker or something like that?
Yeah, if you had like a
Like,
DSC.
Wait a second, because I have.
Yeah.
There's a white
Like,
bar.
one is
because-
They're
heat,
very
and the
different
heat,
temperatures.
Yeah.
and the other
Wait,
is
maybe-
cooling.
Yeah.
Okay.
When you
someone
cool,
compare
like
it,
because
like-
of that time delay in
usually have, like,
reconstruction or rearrangement of
That
the
the
chains.
TG is different.
Yeah, the
And then the
TG.
difference between TG, that's the
Yeah, it could be same related to like the crystallization temperature, and I think usually
you.
they use the crystallization temperature.
Okay. So if everyone can see this.
Yeah.
Alright. So,
no, makes sense.
we
Okay,
have
okay.
room temperature, which is 25 degrees Celsius, right? Now, let's see. Here we have a couple of polymers, right? And these are all increasing in chain length. So, longer length, chain, shorter
It influences
chain
microstructural development.
So the longer the
The
chain
micros-
length. Okay, no, sorry. No,
The longer the chain length, yes. And then these are all the glass transition temperatures for
Okay.
these polymers,
So
right?
the longer the chain length, the lower the glass transition temperature.
Yes.
Okay.
Okay, and that is because there's more free volume because the polymer chains are kind of like a bunch of people with long arms standing next to each other. There's going to be just a little less order and a little less packing for this material.
Oh.
Okay, and I probably should move my phone this way, if that even captures anything. But does it?
Yeah.
I'll just. Yeah. Okay, but what we have here is like basically this undercooling is, say this is undercooling A, and this is undercooling B.
Wait, I thought
And-
that was the what's it called?
Okay. The
quench depth.
I call it undercooling quench depth because this. I
Are
have
they
a-
the same thing?
Kind of. Undercooling is more of like a metals kind of
Oh, okay.
nomenclature.
But here you're relating them as the same thing or
Yeah,
something.
because I don't like quench depth because there's two depths here. There's like the depth at which the squishy layer goes down to.
Yeah, and then the depth of the
And-
film.
And that's the depth of the film. And then there's also now they're saying the depth of the temperature.
Oh,
right?
okay.
Yeah.
So which is why I don't like using
typically
two
in the
words for
DSC, these
like
are-
different
Okay.
things.
Yeah. Okay.
Okay, so let's just
But when
call
you're
this
cooling it,
undercooling or quench depth.
You don't see this peak at the same point because there's been a change,
Equals
so you see it at
quench
the lower. It will
depth.
shift to
Okay.
a lower temperature.
Yeah.
So, and I really wrote that small for y'all sitting there. But basically, this is B. This is the quench depth or undercooling from the second polymer, and this is quench depth from the third polymer. And basically, because these glass transition temperatures are progressively happening at higher temperatures, then as you have a shorter polymer length, you have a higher quench depth.
Yeah.
And because of that higher quench depth, you have more order in your system, and your little squishy thickness, okay, is gonna be a lot less.
Smaller.
Yeah. So this is like squishy thickness.
Right.
Squishy thickness. Okay. And then it progressively just gets smaller, right? And eventually yeah, you just wind up with.
Yeah, when you're very close to TG, then
Yeah.
it's actually.
So that's basically it. Yeah. Is there any more questions? Anything that I could clear up?
Oops, wait, never mind.
Oh, ask me all the questions.
Just repeat what you just said about the squishiness.
Okay, so because the closer you get to glass transition temperatures of your material,
Yeah.
the less ordered your material is going to be, right? The more degrees of freedom your chains are going to have, and that squishy kind of
It increases.
like a rubbery area, that rubbery surface area in your material. This is.
Wait, so maybe my revised question: how does quench depth relate to the squishiness?
Oh, okay.
The smaller the quench depth,
They're
the
investing
more the
compost now.
squishiness.
So the longer polymers
Yeah,
have
so
a
just
thinner
like that.
squishiness.
Have a thicker squishiness.
Okay, thicker squishiness.
Okay, and well, that is because the longer polymers, this is more polymer length.
Yeah, related
Okay.
to the TG. Yeah.
So then the polymer length
Quench.
here relates to the glass transition temperatures, right? So a longer polymer length leads to a smaller glass transition temperature, right? So this could be, say, 30, and this is 35, and this is 40, and this is 45, right? So because it is really close to the temperature with which you're testing it at 25 degrees Celsius room temperature,
Yeah.
this will be more squishy because it is a longer polymer that has less order and that has a lower glass transition temperature.
I think you just use like, let's also use like just the physical values they had on the table, right?
Oh,
So,
yeah.
so I did like, you see these
So
values.
like trying to
Mhm.
draw in
But you see like
buckets.
here, you see go from the metal to the ether to the propel. You see like
Okay,
the
so
Yeah,
longer
yeah, yeah.
But like these two are
Also
not just
track
really
the
about
room
like
temperature
length,
from the
right?
TG
Because the
that,
benzo is like
quench
more.
Yes,
is
that's-
smaller.
yeah.
And
That's, like,
because the quench
overall,
depth
like,
is
bulkiness
smaller,
of the bulkiness.
you have,
So I
right,
think
in the
they
lower
also relate
TG,
like
you
length
have
and
less
also
order
bulkiness.
in the
Mhm.
material.
But like,
and
okay,
therefore
so if
you
you
have more
take these three
squishy.
and you just talk about like
Okay, that makes
the
sense.
length,
Yeah.
then you can just subtract because the temperature, the T they use is 22 degrees.
Mhm.
Yeah.
Right. So if like for
I would also think like, okay,
How long
For-
this is due to the cooling, whatever, undercover?
MME
It's a surface thing.
TG
yeah, it's a
is
surface thing, it's not a bulk
That,
property.
but
So-
then as the squishiness gets larger, as in like
Becomes
the
more of the
the
bulk
longer
effect.
polymer length, okay, yeah, I was gonna say, does it then act more like a bulk? Like,
No.
is it more
the
bulk?
surface gets bigger.
Because the properties are additive in the two-layer model, and the property and that overall property is dependent on what volume proportion each comprises of. So if you have an extension of that squishy layer, your film is always going to be the same thickness, okay?
It's
right?
just the squishy layer.
The squishy layer just gets bigger.
Yeah, it's
Okay.
And
comprising
so
more
because-
of the film.
And because of that, proportionally, you're obviously going to have like more properties pertaining to the squishy.
Okay.
And there's also a good thing that I should note. They kind of tested, on top of chain length, they tested like the bulkiness of the side chains and also related that in like the second to last page. But really, it's all just about like the overall free volume that these chains have. And yeah, that kind of relates a lot to the transition temperature.
so this is like
I have one question.
Yeah?
One of the films were not able to wrinkle or something.
Yes.
So why was that? Was it the icing?
Okay, so there's this graph, and this graph is fun.
Where?
There's this graph right here, right?
Yes.
This graph right here is basically telling you that, all right, this is the film thickness, okay? And at some point, the wavelength goes to 0, right? Which means we get no wrinkling. And this happens at, in this case, for all the films, it happens at a certain thickness, right? It doesn't happen at 0. So, which means that this green, I believe, this diamond pattern one, was the longest chain length. And that happened at the highest thickness, right? So that film was still thicker than all of them, but it didn't fold or didn't wrinkle, which means that when things don't wrinkle, it just basically shows that they're flowy, which means that they're rubbery. So you get to that rubbery region quicker for these materials with longer chain lengths because they're closer to the glass transition
Okay.
temperature.
Okay.
What do we?
Okay.
Oh, yeah.
This one didn't.
So, basically, this green here was, okay, this green here was a longer, can I have a pencil or some shit? Thank you, that's great. So, moving here, and we're basically increasing chain length. Now, with increasing chain length, we get the glass transition temperature gets closer and closer to the temperature that we're testing at, right? Which means that this is also less undercooling. All right, which means, yeah, we're closer to the glass transition for each of these materials. What we see here is that the confinement effects sort of increase, right? With this, basically meaning that the film, that squishy layer gets thicker and thicker. And at some point, that squishy layer, that squishy layer will make up the entire film, right? So if you go down to a certain thickness, we get to like 30, okay, let's just say this. At like 40 nanometers, 80% of the film is squishy, right? That depth-wise, 80% of the film is squishy. At 20 nanometers, like 95% of the film is squishy. At 10 nanometers, all the film is squishy. And because of that, right around here, we have no folding because you can't fold squish. And that's why.
Right.
Pretty much.
Check that out.
You'd think that you could fold squish because it's more flexible.
It's too squished.
Yeah, but then if it's
Two squishies, I don't know.
it's super squish, just like
It's like evens out.
yeah.
Because I think like if something was stiffer, you wouldn't be able to.
But it holds the shape. You can see the wrinkles, I think.
Oh.
Mhm.
Okay.
It doesn't stay wrinkled.
Yeah.
Probably does on its initial push or whatever.
True. Yeah. I guess like people.
Is this all
said
being
when
caught
you
on
wrinkle
camera?
it,
Okay, Jude's knowledge is everywhere. Okay, here we
but,
go.
like slime is squishy and
Yeah.
you can't wrinkle it. Okay. Paper and slime. Love. That's
Yeah, so
all my
basically,
brain.
like for the different PMMA derivatives they use, like the first three are like in order of like increasing tail length, right? So they have the PMMA, PMA, and the PNMPA. And I just took the values from the paper to make it more practical. So they have like 105, 65, 36. And then the T, quench depth is TG bulk minus T. And in the paper, they said the T they use was 22 degrees Celsius, like room temperature. So like, you find that the quench depth for PMMA is 83, 43, 14. So you see that as the tail length is increasing, the quench depth is decreasing, as we mentioned. And so if you relate it to the delta, which is like the thickness of the squishy layer, you see that then they are also inversely proportional. So the closer you are to TG, like a smaller, if your quench depth is 0, then it means you are at TG, right? So the smaller the quench depth, then the bigger your squishy layer, basically. And so that's what I just show. So like, as the tail length is increasing, your quench depth is decreasing, but as your tail length increases, then the thickness of the squishy layer also decreases.
Is the squishy layer that delta you have there?
Yeah, delta. Yeah.
Oh, so
it's-
closer,
That's great.
closer to a TG closer to room temperature is a squishier. Is more
Yeah.
squishy.
Yeah, if it's
Mhm.
closer, but if it's equal to TG,
Then it's super squish.
It's super squishy.
And no wrinkles.
Everything's
Yeah.
squish.
So once
And it's
your
flowy.
once your quench depth is like close to 0, which means your TG minus your T, your TG is 25 or 22. This is 22. Yeah. Then you are very, very like in the rubbery state, and like
Yeah.
TG is like that step function in a DSC. TG is a step function which is it results as a I think it's a competing effect between like changing from that like very crystalline region to now kind of mobile. And so that's how it shows. So like once you get to that point, or once you're getting more closer to TG, then your molecules just want to move around. And I think from the paper they are trying to show that it starts from the thin film or the surface, and then you move down.
Oh, I see.
Yeah.
Because there's more free surface effects at the
top.
Yeah.
Right.
You have like dangling.
And that's the same. Yeah, we are talking about like dangling bonds and all of those things. Like they are just free to do whatever they want.
Yeah.
Yeah.
Okay. Squishy done.
Yeah.
Squishy done. Okay, before we end though, any sort of brainstorming on what kind of questions could be asked?
This paper,
Yeah.
I don't like how they calculated the TG.
Yeah.
Right. They say in the paper, and like I was just reading the materials and methods section. I think how even they were able to measure the modulus, right? It's a question. Because many people don't know you can measure the modulus. Yes.
That way. That was so cool when she did it. I was like, what the fuck?
And even Naomi's one, it's not. They didn't get it as close to what they should actually be doing. So I remember I recommended it to her during one of the poster sessions, because typically what happens is like for very thin films, nano-sized, so you can't just like go and do like an instrument measurement. So they have they clamp it on like some two ends, and then they apply some kind of pressure.
You said it was a vibration.
Yeah. So it could be in different forms, right? It could just be like air, like some high pressure air which causes those vibrations, or whatever form of force that they apply. They measure the wavelength and the frequency of the vibrations, and then they use that to calculate the properties, and that's what they did here. Okay. Right? But more importantly, I think in the last paragraph of their method section, they say to measure the TG, PDMS films were spin cast on clean silicon wafers. The PDMS layer was approximately 12 nanometers thick. Ellipsometry was used to measure the thermal response, right? And I remember I have to go back and review the ellipsometry slides, but I don't remember ellipsometry being Valeria taught us.
Yeah, Valeria
taught us.
I could ask her about it. Yeah.
Yes,
even the postdoc that taught for Sucrup last semester, 2 semesters ago technically. Yeah,
even if it is like, how do I say, it is possible, I wouldn't trust the results too much.
Now I remember all about ellipsometry.
Yeah, ellipsometry is used for refractive index. You can calculate thickness, but for TG, because they say TG was determined from changes in the thickness.
Yeah.
Right. So how
changes in the thickness?
Yeah, but how sure are you even those changes in the thickness measured were accurate?
It says TG was measured, changed the thickness upon cooling.
Yeah.
That's weird.
Wait, how can they even measure that?
And that's what I was saying, because the undercooling thing we are talking about,
did they measure thickness from the refractive index?
No, they said thickness.
They measure.
Why don't they just measure the refractive
they change
index?
temperature. So they cycle from TG to melting, and they look at the refractive index.
No, they look at the thickness.
No, it doesn't. Well, they use something from lexometry. I don't know what.
Yeah.
Yeah.
They say it's just weird that they mention film thickness.
They mention thickness, and that thickness could be gotten from some refractive. But
that's the thing,
how they do it, I don't trust it.
That's HF. That includes the squishy plus.
But
the whole thin film.
Yeah. This should be for all of this specific polymer, right? Not for these thin films. TG.
I'm looking at the polarization of light risk mixer.
This TG.
You would think it would be because the chain reordering causes a difference in the refractive index.
That's what I first thought.
Mm-hmm.
And so this is what this gets, right? if you were to look at this, it's like the change in polarization as light reflects or transmits through material structure.
Check if like ellipsometry can be used to measure TG and how they do it.
Alright. Ellipsometry.
Yeah, because like
They're related.
the paper is like really focused on like TG and modulus, but if we can't like
Ellipsometric
be sure
angles
about
on-
how that is done, yeah.
Simply,
It's not direct.
it can.
Mhm.
And it depends on the ellipsometric angles, which
Yeah, those are like some crazy equations. You remember?
I think
the
so.
ellipsometry.
Yeah. And they
Yeah,
depend
so-
on a ton of shit too.
Yeah, yeah, it depends on a lot of things. That's why I'm saying like I don't trust like what they did because they don't talk about all those other things.
And that's how they measured the glass transition temperature.
Yeah.
Just want to call it
Glass
thickness.
glass transition temperature is an ass anyway. No one even knows like when to describe where it happens.
Okay,
So
maybe that's why they're just doing this catch-all term of thickness.
they should have done glass transition temperature.
Oh, they use density.
They use the-
Calculate
Okay.
density.
They
Apparently.
get density from the refracted light. Is that basically it?
I'm trying to understand something.
That's what it was.
DC.
Yeah, cooling from the rubbery state
Yeah,
into the glassy
secret.
So
state. Yeah, that's
relating
what I
this
said.
to elastic modulus is like
The
more
secret
squishiness,
paper.
worse than elastic modulus.
Basics of what's up.
Yes. So say
Ah,
you
yes,
had-
density.
More squishiness is less
Mm.
elastic.
Yeah, yeah.
Standard
I'm
Yeah.
just like we didn't get to, or like I'm trying to relate what we just
Yeah,
did.
but
I,
That's just
Yeah, and that's the thing because we
Basic
didn't even talk
mechanics
about
is like if you have something
the
squishy, you're not
modulus
gonna-
because like the paper is literally about modulus, but
Yeah.
we're talking about the squishy layer a lot. Yeah, but it's kind of
more squishy
intuitive.
layers, so longer chains have a worse.
Yeah.
elastic
Yeah.
modulus.
and it all depends on like how much that
Linear
squishy.
expansion
So like
coefficient.
So I think what they say in the paper is like as we were saying
Let me use my skill.
from TG, they said like yeah maybe the
Oh, they
Say
find the
another.
thermo-optic coefficient,
okay.
Okay.
which then can be related
Okay.
to
This is like 50-50 squishy.
a
and this is
reference
surface.
Yes.
Okay.
This is
To the
squish,
TG.
Yeah.
right? As squish
No,
decreases,
I'm talking to the
right?
Yeah.
And proportionally, this material is
They
stronger.
find
Yeah,
the
yeah, yeah.
linear
And that's what it
coefficient
is.
of
Okay,
thermal
yeah.
expansion.
I just like
How much it expands.
I just wanted
And when it expands,
I just
they
wanted to
use-
confirm that.
No, but that's
because
still
I-
not like
I'm
that's
not
still
gonna
cannot
sit
be
around
related to
and feel
TG.
deeply.
Like
It
that,
is.
It's super
Basic understanding.
That's
of
not
linear
direct.
motion is something
A
that is
direct
usually
relationship.
Very
have a lower
complicated.
elastic modulus.
And
this
This is
is
like
a
the
recent
lowest brain
paper.
And that's why I
I've
think
seen
I
out of
actually
this group
think
so far.
people say it
Really?
might be
Yeah.
chaotic
When I
because
read
of
it,
the
I thought it
WLF.
was
I also think
pretty
it could be
easy.
my
I was
advice.
like, oh, I think I'm understanding
staying
it, but then you went
Because
through all the
we
now
do a
we're
lot of
talking about,
DSC
like, all this
things.
stuff, and I'm like, I don't know.
And
Can
if
I don't know if I know
she
this paper well enough to
is
go
not
into
really
it.
excited about how they
Like, I
did
don't know
the
what kind of
TG
questions
stuff.
we asked.
They just-
And
It
it was
would
like
be a
TG,
question.
TM.
Yeah.
So then what do you
Do you think they would
say?
ask
Like,
because I also was like,
they
oh,
should have
you
just
mentioned
used
time
DSC
superposition.
to
I think they
measure
were definitely gonna
the
ask
last
about
transition
that, right?
temperature.
Yes, they could
Time
use
temperature
DSC,
superposition.
but
And they're gonna
I
say
think like
maybe-
But they say that it
there
doesn't
might
relate
be
to
a
those
way. They
concepts.
might not say. Okay,
But they're
maybe
like,
this was a
in what
bad
case would it
method,
relate,
even though they
right?
can say that they
Kind
can say
of thing.
okay,
Uh,
how
Or
should
like,
they
oh,
measure
for
the
this
TG?
polymer,
Right.
at what
And so
like
we
thickness
need
do you
to,
think
as
it
you
would
are
really
saying,
go
maybe they
around?
use a linear,
Or
but we need to
something
be
like that,
sure what
at that
exactly
temperature,
or how
you know,
exactly that can be done
Right.
to be able to make
Yeah.
a
So, and then
logical.
I guess it could also
explanation.
be about
So I would
like,
also
the
go through
reason
like
why
my
glass transition
ellipsometry
changes
notes.
with
And if I
crystal
find
structure,
something,
or like
because I remember
Oh.
molecular
ellipsometry,
structure,
there is a lot of
right?
equations.
So
and
that could
you
also be a
write the
question
Oh,
code and
with the
just get
dangling
stuff.
ends.
Okay,
and,
there's
like,
some
there's less
delta
order.
T. I don't know what delta T is,
with
but there's
the
a
glass
point.
transition
I'll-
and the
I can send this in the
molecular
chat.
structure,
Yeah.
what
But it
happens
says
is
this, you
and I
can
had to look
extract
something.
it, extract whatever the parameter is from ellipsometry.
Because I
Whatever
always
it
thought
changes,
that,
that's your glass
and this is a strange thing, right? Because I was looking it up.
Yeah, that
that checks
They were
out.
like-
I don't know how they
makes
get the
sense.
delta.
I always
makes
knew that a
sense.
longer
Yeah.
chain
Oh, it's an
and a
ellipsometry.
higher molecular weight
Symmetric.
would mean like
Yeah,
a
that would
higher
make
sense. That
melting
would make sense,
temperature,
and that's
right?
my
And I
point.
thought that because
Okay.
it's a
There's
higher
a lot of
melting
things
temperature, it would be a
about
higher glass
ellipsometry,
transition
but
temperature. So I was like,
I
what the
feel
fuck,
like
right?
in terms of
So what
Yeah.
ends up happening
Okay.
is
aside how they
although
calculate
at melting, these
they actually
bond,
cause a
these
wrinkling,
this
this
okay,
is
so
another
like
question they could ask
fucking
because they don't show a lot
right?
of AFM stuff.
Yeah.
So it's really not
They don't.
about that.
No.
It's
So
really about
if you
the
had like a
TG
million
and
of these
the-
shits,
Yeah.
right?
Right.
These things would totally fucking get in the way,
Yeah.
right? Of melting,
Yeah.
right? Because then they're all kind of like
Oh,
it's like
this
everyone's
is
kind of like
the shit you're talking
intertwining
about.
arms and like
Oh.
kind
Are you
of.
doing this now?
No, I don't think we're doing anything else anymore.
No?
Okay, I think we could just stop recording then.
Oh yeah.
We
Yeah.
technically don't have this.